So we are going to do number 3 together. Okay, we'll just jump to number 3. So it says, a ship sails 50 miles on a bearing of 20 degrees, then 30 miles further on a bearing of 80 degrees, find the resultant displacement vector as a distance in the bearing of this vector. Okay, so, reminder from yesterday. Bearing. What is that telling me? What's a bearing? What does that mean? He's flying on a bearing of 20 degrees. What does that mean to you? 20 degrees east of north. It goes clockwise from true north, right? So is that the same as theta? No. Okay. This right here is your, see, bearing is 20 degrees. So this is your beta, right? And then 30 miles further on a bearing of 80 degrees. So this is like beta 1 and beta 2. But I need theta in order to do my drawing even and to do my calculations. So how do I find theta if I know the bearing? How are those related? Talked about it in map time yesterday. Or just think about it. If I have true north, right, and I'm on a bearing of 20 degrees. Oh, I won't draw. 20. Yeah. How do I find theta? 90 minus beta, right? So if you need to draw yourself a little picture, wrap your mind around it, there you go, if you don't remember what to do. So I know that my first theta is just 90 minus that first beta, which is 20. And my second theta is 90 minus, what was it? 80, which is going to give me 20 and 70. Okay. 10. 10. Oh my gosh, 10. Good Lord. Yeah, I'm really starting off well, aren't I? Okay, 10. It's 10. It's not 20. If I can't even subtract, did I subtract the other one right? Yes, I did. Okay, good job. Yay me. Didn't subtract numbers. All right, so there are my two angles. Now, this is where maybe having a picture so you can wrap your mind around it. If you're going to do it what I would consider the hard way, easy way, hard way, that's a matter of opinion, then it might help to draw pictures. And so let's, on the graph paper, just so you have an idea of what's going on, and regardless of which way it is. So if I'm going to take this, my ship sails 50 miles on a bearing of 20 degrees. Now, when I go to draw this, I don't really care if my 50 is super accurate, you know, the length of it or whatever. I don't really even care that my 20 or my 70 is 100% accurate. It's just getting me an idea of what's happening, okay? So if I think about, one of the reasons the graph paper helps is you can see where, like, true north is and where the x-axis would be if you were thinking about it being at 0. So if I'm going to start here, and I'm going to go 50 miles on a bearing of 20 degrees, then I could say that, we'll make that 50. That doesn't even look super accurate for 20. But here's my bearing of 20, which means that this angle right here would be 70, and this is 50. And I'm not even going to label my angles just yet, but I'm going to show you why the angles might be helpful. Then I go 30 miles further. So if I want it kind of accurate, then I would at least want my next one to be shorter than 50, since 30 is smaller than 50. And a bearing of 80 degrees means that it's going to be a whole lot farther. It's going to be like this, maybe. Okay, I don't know if that's shorter, but come on. So maybe like that. And that could be like 30. So then I want to find the resultant displacement vector and the angle. So if I draw this in there, it gives me an idea of the length and the direction, okay? Now, I can use law of sines or law of cosines here. It's not what we're going to do, because that's what I would consider the hard way, because now, in order for me to do that, I have to reason through what the angle measures would be, which is possible. And I just want you to see that, because these things could come up in other situations. If I know that this angle from here all the way to the purple line is 70 degrees, right, because that was 20. Okay, so if this is 20, you see this, like, these are parallel lines right there, right? So if this is 20, right, from this perpendicular right here, then that means that my alternate interior angles here, like this This is 20 plus that 90, and this is 70. This one would have to be 70 right there. And then this is 10. I can get that angle right there, which is the same as my 90 plus that 20. So this is 110, and this was that 10. Does that make sense to you? 110 here, because that's what this would be. And this is 10, so this whole angle right here would have to be 120 degrees. If I know that much, and I can reason through that, can I find my resultant vector right now using the law of cosines? I totally can, right? I can find it doing the law of cosines. Then I can also find this angle, right? So if I find this angle measure to actually find my new bearing, once I got that angle measure, what would I do with it to get my actual bearing? Think about that. If I found this angle, what would I do with it? Because I'm looking for the length of my green vector, and I'm looking for the bearing of the green vector. So I would be looking for, if this is true north, basically this angle here. Do I already know this part? So once I found that, couldn't I just add it to that one? Does that make sense to you? So if you can understand the triangle, you can reason through that regardless of whether or not you know anything else. Now, would you like a better way to do that? So you don't have to reason through those angles, because those angles can get confusing in those triangles. And that's what I was thinking the whole time, like, I get this and I can label this, and wow, you can really get lost in this, and this is confusing. And then that's when I realized I was doing it the hard way. Well, here's the thing, is that I know if I can find the actual component vector, the component form of my purple vector, and the component form of my pink vector, can't I just add those two together to get the component form of the green vector? Would you agree with that? Isn't that what we did before? If I can get this in this form and this one in this form, and then can't I just add them together? That's why we were doing it. Do I have enough information to find those things? I do, don't I? If I go back here, if I have the magnitude and the length, how do I find the actual component? What do I do? You can look back at your notes from yesterday if you need to. If you have the magnitude and the amplitude, or the magnitude and the direction, how do you find the component form? What do we do there? I'm sorry, what? I use tangent, is that what you said? Okay, I use tangent if I have the component form. Remember, your component form is this. I want to get to that. I don't have that. I have this 50 miles here represents the magnitude of, we'll say, vector A. We can call them A and B. Vector A. And then this is the magnitude of vector B. So I have the magnitude and the amplitude, because tangent would give me theta if I didn't know it. I know the magnitude and I know the amplitude. How do we use those two things to get it into a component form? What is your x value? Look down at the bottom of the front of those notes. R cosine theta, R sine theta, right? So if I call the first one A and the second one B, then for vector A, to find that, that's going to be 50 times the cosine, not of 20, but of theta, 70. You have to use theta or you're not going to get the right things here. And then 50 sine of theta, which is 70. What would it look like for vector B? 30 what? Cosine of what? 10. And then 30 sine of 10. To get it in that component form. So we're going to do these. We're going to put them in the calculator. And I want to store all that stuff. So since I have 2 parts for A and 2 parts for B, basically, first of all, check that you're in degree mode. And then you can decide to store them however you want. Me storing them in X and Y isn't going to do me any good because I have 2 X's and 2 Y's. If I want to call them A and B, I also have 2 A's and 2 B's. So the easiest thing for me is if I'm going to do A and I need another part for A, I just do the one right underneath it so I know they're both A. So I can do it like XY type of thing. So I'm going to do 50 cosine of 70. And I can do this all at once. If I close my parentheses there, I can say I'm going to store that in A. And that way you don't have to do it and then store it. You can do it all in one step. And then I'm going to do 50 sine of 70. Close my parentheses. And I want to store that in D because it's right underneath A. So I've got those, right? And then I'm going to do the same thing for the 30. So 30 cosine of 10. I'm going to close my parentheses. I'm going to store it. Oops. I'm going to store it in B. And then 30 sine of 10, and I'm going to store it in E. Okay. So what I have here basically, it's going to disappear, but you can write the decimal. I can't write them down and look at them, and I should have done them one at a time if I was going to write them down. But I have all that stored. That means that gives me my two components. What I just found is this ordered pair for this vector and the ordered pair for this vector. If I want the ordered pair for the green vector, what do I do with all that information? Add them together. So I'm going to go back over here and I'm going to add them, right? What do I add my A to? What did A represented the x value of A, right? So I need to add it to B. So I'm going to do alpha A plus alpha B. Now this one, where would it be good to store it in? I could store it in C. And does this represent it represents the x value. So you could store it in C if that helped you. I'm going to store it in X because I'm actually going to store it in X and Y this time. But again, it doesn't matter as long as you know where your stuff is. And then I'm going to write some of this down just so that I don't lose total track of what I have. So what we have here then is for my resultant vector. This was 46 something. I don't even remember because I clicked away, but it's something like that. And it doesn't matter because I stored it. And then I'm going to add the D plus the E because those were my Y values of my two vectors. And I'm going to store that in Y. And that gets me 52 something. Now, is that my answer? Did it ask me for that? It didn't ask me for the component form. What is it asking me for? The resultant displacement vector as a distance and a bearing. So I need to get it back into the magnitude and amplitude type of version. So how do I find the magnitude of this? How do you find the magnitude when you have the component form? Good. Square root of x squared plus y squared. It's basically Pythagorean theorem. So I can come back over here, and I can just do, since I stored it, and if you called it C and whatever, just make sure you're using the right letters. I do the square root of x squared plus y squared, and that gives me 70. Gives you a nice, pretty number. Does a nice, pretty number kind of throw you off a little bit? Threw me off, too, when I did that. I was like, wait. Okay, but it just, oh God, I must have done something wrong, right? But it works. So the magnitude is square root of, and it's okay just to put this, at least this is something, right? And that is equal to, so we get 70, but then I have to have some sort of, I can just say 70. It's 70 what? Miles. Okay, so it has to match whatever this is. It's 70 miles. There you go. So now, how am I going to find the amplitude? Yes, good. Arctangent of y over x, right? That's where the tangent comes into play when you're looking for the angle. So I'm going to do tangent inverse, and it's y over x, or whatever you stored them in. I stored them as y over x so that I wouldn't mess any of this stuff up. Alpha y divided by alpha x. Not alpha. I don't need to do alpha x. I do that every time. And that gives me 48.213. Okay, so I get 48.213 degrees. But what is that? What does that represent? Is that my answer? No, this is my theta. Do I want theta? No, I want beta. I need the bearing, right? So what do I do with this? Subtract it from 90. The bearing is 90 minus theta. Just like theta is 90 minus the bearing. So you could store this if you want, but you can just do 90 minus the answer, and you get 41.787. So the bearing is 41.787. If we hadn't have stored our numbers, you think we'd have gotten a nice pretty 70? No, we wouldn't have, right? But since it stores everything, it cleans it up for you when you get it that way. So here's the thing. I wasn't trying to confuse you at the beginning with showing you the picture and thinking through all that, but I wanted you to see that you can put it together and you can use law of sines and law of cosines that way. And sometimes with the applications you need to, depending on what they're giving you, if you're talking about two forces placed on one object, which is something that we'll probably look at tomorrow on one of those assignments. But all you have to do is understand how to put it in the component form, get the component form of the resultant, and then take it back out. And it's the easiest way to do it. Okay? So at least I want some sort of little sketch, whether you use the graph paper, because it helps you make sense of this. Plus, when you look at this, this is not to scale really at all. The only way it's really to scale is that my 30 is shorter than my 50, and I kind of went in the right direction. But I didn't worry about it and get a protractor out and make my angles beautiful or anything. But I know that if my answer was like a bearing of 120 degrees, I think something's wrong, right? Because a bearing of 120 degrees would be like way over here, and my vector's here. So at least can give you an idea of a reasonable answer. Since our bearing was 41 degrees, I can see that. Plus, it's got to be bigger than what the bearing was before, right? And your length has to be longer, you know, than whatever, just for you to get an idea of what's going on. Okay? We good? Any questions? All right. So I'm going to give you a paper that has two more of them worked out. It pretty much does the exact same thing, but just if you needed something else to look at. You will have some of these, like look at number 4. You have a bearing of 290 degrees. Well, when you do 90 minus 290, what kind of answer are you going to get? Negative, right? Can you take the sine and cosine of negative angles? Think about that. You can. So it wasn't a trick question, but you can, right? Because the negative angles have this can be a positive angle. It's fine to leave it negative. In the end, your answers really should be positive, and you want them in the positive form. But if you're using them in your problem, as long as they're the correct angles, then you're fine. Okay? So it's all good. If it makes you feel better to put it in the, in the positive form of it, it's fine as long as it's the same angle. Okay?